Welcome to the chapter Motion.
This slide presents the overview of the chapter. Learning objectives. By the end of this chapter, you will be able to
understand the concept of relative motion, differentiate the distance and displacement, draw the displacement vectors, define the average velocity and average speed, discuss about the uniform and non-uniform motion, explain the term acceleration, derive the equations of uniform accelerated motion, discuss the graphical representation of motion, explain the equations of motions by graphical method.
Introduction. Before entering into the chapter, follow the instructions shown on the screen. Click each tab to know more.
Generally, we have seen many examples of motion around us, like motion of people, vehicles, trains, aeroplanes, objects thrown into air, etc. We know that it is due to the motion of the earth that the phenomena like sunrise, sunset, changes in the seasons, etc. occur. Do you know what causes the phenomena of sunrise, sunset, and changing of seasons? If Earth is in motion, why don't we directly identify the motion of the Earth? To find out the answers to these questions, we need to understand the terms relative and motion. What is relative? We use many statements in our daily life to express our views. The meaning of a statement depends on the relation between the words used in it. For example, observe the statements on the screen. The words have a perfect individual meaning. Both the statements are constructed using the above words. But the statement 1 has a no proper meaning or sense, and the statement 2 has a perfect meaning and makes sense. This is because the words plate and gaseous have no relation, and the words plate and circular have a relation. That means relative to plate, the gaseous is not related, and relative to plate, the word circular is related. A statement has a meaning only when there is a relation between the words. So finally, we can state that the meaning of a statement depends on the relation between the words used in it. Let us now learn about the term relative with respect to the positions. There are two typical sets of position. They are right and left, up and down. A real-life example. Click each tab to know more. Right and left. For example, let us consider that two persons A and B are moving opposite to each other. For the person A, the house is on the left side of the road, and for the person B, the house is on the right side of the road. Thus, the position of the house is relative to the observer, that is clearly when speaking of the left and right of a person. Up and down. For example, consider a ball in spherical shape and fix 4 pins on it in all the 4 directions and name them as P, Q or S. In P point of view, the position of pin P appears up and the position of pin Q appears down. But in the view of pin Q, it appears exactly opposite. In the same way, the directions of up and down are not the same for the pins R and S. They change with the position from where the pins are observed. We know that Earth is a sphere, so the upward direction of the vertical position on its surface depends upon the place on the Earth's surface, that is the place where the vertical is drawn. Hence, the notions up and down have no meaning unless the point on the Earth's surface to which they refer is defined. A real-life example. The question, is it day or night, cannot be answered without indicating the point on the globe. Consider 2 points on the Earth's surface A and B, in a way that A is in the day part and B is in the night part. For the same question, the person at A says it is day and the person at B says it is night. The simple fact is that day and night are relative notions and the question cannot be answered without indicating the point on the globe where the question is being asked. To understand the idea of motion, let us take the following hypothetical activity. Observe the conversation between 2 persons who stand beside a river. What is the state of motion of the mountain? It is at rest. What is the state of motion of the boat? It is moving due south. What is the state of motion of the persons in the boat? They are also moving like boat. How do you decide that the boat and the persons in the boat are moving? With respect to us, the position of the boat and the persons are changing with time, so they are in motion. Now, observe the conversation between the persons sailing in a boat. What is the state of motions of both the persons who stand beside a river? They are moving due north. What is the state of motion of the mountain? It is also moving due north. What is my state of motion? You are at rest. What is the state of motion of the boat? It is moving due south. From the discussions, it is clear that the motion of an object depends on the observer. So motion is a combined property of the observer and the body which is being observed. Definition of motion. A body is said to be in motion when its position is changing continuously with time relative to an observer. Note: let us perform an activity for drawing path and distinguishing between distance and displacement. Click each tab to know more. Take a circular object like a ball. Throw it into the air with some angle to the horizontal. Observe its path and draw it on paper. We observed the path taken by the circular object when it was thrown into air and the length of the path traversed by the object. In this activity, we learned that the length of the path traversed by an object in a given time interval is called distance, and the shortest distance covered by the object in a specified direction is called displacement. To describe a physical situation, some quantities are specified with magnitude as well as direction. Such a physical quantity is called a vector. The physical quantity which does not require any direction for its explanation is called scalar. Here, PSQ shows the actual distance covered by an object and PQ is displacement, which is a straight line drawn from initial position to final position of the object's motion. The physical quantity which has magnitude and direction is known as vector, and the physical quantity which has magnitude and do not have direction is known as scalar. Therefore, we conclude that the distance is a scalar and displacement is a vector. The SI unit of the distance or displacement is meter and is denoted by m. In the same way, kilometer, centimeter, etc. are also used to express this quantity. Because 1 kilometer is equal to 1000 meter, 1 meter is equal to 100 centimeters. Drawing displacement vectors. Consider a person standing at point P and moves x kilometers towards point Q located in east along PQ, and then after reaching at point Q, he starts moving along QR a distance equal to y kilometers due north. The actual length of the path traveled by the person to reach point R is the length of PQ plus the length of QR. So, x plus y kilometers is the distance traveled by him. Already we know that distance is scalar quantity and its value can never be zero or negative during the motion of the body. In the same example, join the point P and R to know shortest distance. The length of the straight line PR is the displacement from P to R. Thus, the displacement represents the shortest straight line path between the initial and the final positions. Here, the displacement can be found by using the Pythagorean theorem or hypotenuse theorem. Displacement is a vector quantity and it can be positive or negative or zero. Note: the distance covered and the displacement are time-dependent quantities. Suppose a person again travels from R to P, comes back to the original position. Then the person has zero displacement even though he was moved through a distance. Because the person moves back to his original position, that his final position coincides with the initial position. Let us consider the real-time example to understand the average speed and average velocity. Suppose a bus started at point A and reached point B, which is at a distance of 450 kilometers in 9 hours. Here, the distance covered by the bus in each hour is equal to 450 kilometers per 9 hours, which is equal to 50 kilometers per hour. But the bus does not cover exactly 50 kilometers in each hour, because there may be some variations in distance covered by bus for each hour. So we take average of distances covered by the bus for each hour to decide its average speed. The distance covered by an object in a unit time is called average speed. Let the displacement of the trip in this example be 270 kilometers due southeast. The displacement in each hour is equal to 270 kilometers per 9 hours, which is equal to 30 kilometers per hour. The displacement of an object per unit time is called average velocity. Average velocity is vector and is along the direction of displacement. The quantities average speed and average velocity explain the motion of a body in a given time interval. They do not give any information about the motion of the body at a particular instant of time. Numerical problems. Vinay swims in a 60-meter long pool. He covers 120 meters in 1 minute by swimming from one end to the other and back along the same straight path. Find the average speed and average velocity of Vinay. Click the tab to view the solution. Instantaneous speed. For example, we can tell the speed of the bike at any instance by looking at its speedometer. The speed at any instant is called instantaneous speed. Definition. If the speed of a body changes continuously with time at any instance is called instantaneous speed. The instantaneous speed at a given point is equal to the ratio between sufficiently small distances over a part of the path which contain the reference point and the corresponding small time interval. Speed and velocity. Every object in motion has both velocity and speed. Consider a car moving along a straight road with varying speeds. The motion of the object can be described using distance versus time graph. In this graph, time is taken along the x-axis and distance is taken along the y-axis. From the graph, it can be observed that in time interval t1 to t2, the car traveled the distance equal to s2 minus s1. Then the average speed of the car is s2 minus s1 by t2 minus t1. Speed gives the idea of how fast the body moves. In general, bodies move in a particular direction at an instant of interest, and this direction may not be constant throughout the journey. So, we need to define another quantity called velocity. Velocity gives the idea of how fast the body moves in a specified direction. So, it is a vector. A vector can be represented as a directed line segment. Its length indicates magnitude and arrow indicates its direction. If a body moves in a curved path, the tangent drawn at a point on the curve gives the direction of velocity at that instant. Let us perform an activity for observing the direction of motion of a body. Click each tab to know more. Take an object which is tied to the string at one end. Try to rotate the string in a horizontal direction as it makes a circle. Now, release the string at any point on the circle. Observe the direction of motion of the object. Repeat the same procedure for different points. We will observe that the object will be moving in a straight line with respect to the released point. Similarly, we also observe that the direction of motion changes at every point when the object was released. From this activity, we learn that on being released, the object moves along a straight line tangential to the circular path. This is because once the object is released, it continues to move along the direction it has been moving at that instant. The direction of velocity is tangent to the path at a point of interest. The SI unit of velocity is meter per second. Let us know about the uniform and non-uniform motion. Consider a moving vehicle or bicycle which covers a distance 5 meters in the first minute, 5 meters in the next minute, 5 meters in the third minute, and 5 meters in the fourth minute. In this case, the moving vehicle covers 5 meters each minute. As the object covers equal distances in equal intervals of time, it is said to be in uniform motion. Suppose a moving vehicle or bicycle covers a distance 5 meters in the first minute, 6 meters in the next minute, 5 meters in the third minute, and 4 meters in the fourth minute. In this case, the moving vehicle covers unequal distances each minute. As the object covers unequal distances in equal intervals of time, it is said to be in non-uniform motion. If the direction of motion of the cyclist is assumed to be constant, then we conclude that velocity is constant. The motion of the body is said to be in uniform when its velocity is constant. Numerical problems. A man standing under a lamp of height h above the ground starts running with a constant speed v in a constant direction. The light from the lamp falling on the man forms a shadow of him. Find the velocity with which the edge of the shadow of the man's head moves over the ground if his height is h. Click the tab to view the solution. Let us perform an activity for observing the motion of a ball on an inclined plane. Click each tab to know more. Set up an inclined plane. Take a ball. Push it from the bottom of the inclined plane with a speed so that it moves up. Observe the speed and motion of direction of the ball. Now, release the ball from the top of the inclined plane. Once again, observe the speed and motion of direction of the ball. We observe that the speed of the ball increases gradually on the downward slope, but the direction of motion remains constant. Decreases gradually on the upward slope, but the direction of motion remains constant. In both the cases, we learned that speed of the object will change on the inclined plane, but the direction of motion of the object remains constant. Let us perform an activity for observing uniform circular motion. Click each tab to know more. Take an object which is tied to one end of a string. Try to rotate the string in horizontal direction as it makes a circle. Now, draw its path of motion and velocity vectors at different positions. Assume that the speed of the object is constant. observe the velocity of an object. We will observe that the object will be moving in a circular path with constant speed and the direction of velocity changes at every instant of time. Finally, we have learned that the direction of the velocity at any point is given by the tangent to the circle at that point during circular motion. The direction of motion is therefore continuously changing, but the speed is constant. As we know that the direction of velocity is tangent to the path at a point of interest, so the velocity is not constant. In this activity, we learned that though speed remains constant, the velocity of the object changes continuously, because magnitude of velocity is constant along the circular path. The only change in its velocity is due to the change in the direction of motion. Let us perform an activity for observing the motion of an object thrown into air. Click each tab to know more. Take a ball. Throw it into the air while making some angle. Observe the speed and motion of direction of the ball. Observation. We observe that the speed of the ball decreases on upward slope and increasing on the downward slope, and the direction of motion also changes continuously. From this activity, we learn that the speed and the direction of motion both change simultaneously. From the last three activities, Activity 3, Activity 4 and Activity 5, we conclude that the change in velocity takes place in three ways, such as speed changes with direction remaining constant, direction of motion changes with speed remaining constant, both direction and speed changes simultaneously. The motion of an object is said to be non-uniform when its velocity is changing, and the motion of the object is said to be in uniform when its velocity is constant. Now, let us learn about acceleration in detail. We learned that the velocity of an object can be changed by changing its speed or its direction of motion, or both. In either case, the body is said to be accelerated. Acceleration gives an idea how quickly velocity of a body is changes. We experience acceleration many times in our day-to-day activities. For example, let a train start from rest at station A. When it starts moving, its velocity increases, and after a certain time interval, it attains a constant velocity. As next station approaches, its velocity gradually decreases and finally becomes zero at station B. This rate of change of velocity of an object is called acceleration. Here, we can say that the term acceleration not only applies to increasing velocity but also to decreasing velocity. The decrease in speed as the body moves away from initial position is called deceleration. Deceleration can also be called the negative acceleration. As per the definition, the formula of acceleration of the body is shown on the screen. If the velocity of an object changes from the initial value u to the final value v in time t, then the acceleration a is v minus u by t. This kind of motion is known as accelerated motion. The acceleration is taken to be positive if it is in the direction of velocity and negative when it is opposite to the direction of velocity. Acceleration is also a vector and is directed along the direction of change in velocity. The SI unit of acceleration is meter per second square. If an object travels in a straight line and its velocity increases or decreases by equal amounts in equal intervals of time, then the acceleration of the object is said to be uniform. The motion of a freely falling body is an example of uniformly accelerated motion. On the other hand, an object can travel with non-uniform acceleration if its velocity changes at a non-uniform rate. For example, if a bus traveling along a straight road increases its speed by unequal amounts in equal intervals of time, then the bus is said to be moving with non-uniform acceleration. Now, let us derive the equations of uniform accelerated motion. Consider the motion of an object along a straight line with constant acceleration. Then, the acceleration of the object is shown on the screen. Let u be the velocity at the time t equal to 0 and v be the velocity at the time t, and let s be the displacement covered by the body during time t. Therefore, the uniform acceleration is shown on the screen. Acceleration A is equal to v minus u by t. Then A into t is equal to v minus u. That is, u plus at is equal to v. Consider it as equation 1. Since the acceleration of the body is constant, hence the average velocity is equal to v plus u by 2. But we know average velocity is displacement by time taken. So, we can write it as v plus u by 2 is equal to s by t. Consider it as equation 2. We get the following equations by solving the equations 1 and 2. Here, we get the equation ut plus half at square is equal to s. Consider it as equation number 3. By solving the equations 1 and 3, we get the following equations. Finally, we get the equation v square minus u square is equal to 2as. Consider it as equation number 4. The equations of uniform accelerated motion are shown on the screen. Note, if the speed of an object increases, the direction of velocity and acceleration are one and the same. If the speed of the object decreases, the direction of velocity and acceleration are in opposite directions. In such a case, at a certain instant, speed becomes 0. If there exists an acceleration of a body at a point where its speed becomes 0 for an instant, then the body returns in the direction of acceleration and moves continuously, like in the case of stone thrown vertically up into air. Now, let us study a few important points that ought to be remembered while using the equations of motion. The following points are to be remembered while using the equations of motion. Choose origin on a straight line. The quantities directed due right are taken as positive and due left are taken as negative. Expressing the displacement with proper sign is important. Displacement is positive while measured along the positive direction and is negative while measured along negative direction. Let us do a lab activity to find the acceleration and velocity of an object moving on an inclined track. Click each tab to know more. The aim of this activity is to find the acceleration and velocity of an object moving on an inclined track. The materials used in this lab activity are glass marbles, long plastic tube, digital stopwatch, books, steel plate. Take 2 books. Place them on a table. Take a long plastic tube. Cut it in half along the length of the tube. Mark the readings in centimeter along the length of the tube. Now place one end of the tube on the books and the other end on the table to make an inclined track. Now take a steel plate. Place it at the bottom of the track. Take a marble having enough size to travel in the track freely. Now release the marble freely from a certain distance 20 centimeters and start the digital stopwatch simultaneously. Stop the digital stopwatch when sound is produced. Repeat the same experiment for same distance 2 to 3 times. Note the values of times in the observation table. Find the average time and 2s by t square for every trial. Draw the distance versus time graph for all values. In this activity, we observe that for every trial, the average time and the acceleration remains the same. With no change in the inclination, initial velocity and the distance traveled, there will be no change in the time taken for the travel and the acceleration during the travel. Numerical problems. Starting from a stationary position, Shravan paddles his bicycle to attain a velocity of 3 meters per second in 60 seconds. Then, he applies brakes such that the velocity of the bicycle comes down to 4 meters per second in the next 4 seconds. Calculate the acceleration of the bicycle in both the cases. A car travels from rest with a constant acceleration a for t seconds. What is the average speed of the car for its journey if the car moves along a straight road? A particle moving with constant acceleration of 3 meters per second squared due west has an initial velocity of 9 meters per second due east. Find the distance covered in the 5th second of its motion. Click the tab to view the solution. Let us know the graphical representation of motion. Generally, newspapers and magazines use different types of graphs to present the information in an interesting way. They often use bar graph, pie charts and line graphs which provide greater details of the information and make the information more interesting. To describe the motion of an object, we can use line graphs. In this case, line graphs show dependence of one physical quantity such as distance or velocity or another quantity such as time. Now, we will discuss about the distance time graph. To draw the distance time graph for the given data, take a sheet of graph paper and draw two lines perpendicular to each other on it. Now mark the horizontal line as XOX'. It is known as the x-axis. Similarly, mark the vertical line YOY'. It is called the y-axis. The point of intersection of XOX' and YOY' is known as origin O. Decide the quantity to be shown along the x-axis and that to be shown along the y-axis. In this case, we take the time along the x-axis and the distance along the y-axis. Now choose a scale to represent the distance and another to represent the time on the graph. For the motion of the car, the scale could be x-axis 1 centimeter equal to 1 second and y-axis 1 centimeter equal to 5 meters. Mark values for the time and the distance on the respective axis according to the scale we have chosen. From the table, the set of values for time and distance are 0, 0, 1, 5, 2, 10, 3, 15, 4, 20, 5, 25, 6, 30, and 7, 35. The first number of the set represents time and the second number represents the corresponding distance. To mark the set of values 0, 0, look at 0 on the x-axis and 0 on the y-axis. This point is the origin. To mark a point for the set of values 1, 5, look for 1 on the x-axis and draw a line parallel to y-axis passing through this point. Look for 5 on the y-axis and draw a line parallel to x-axis passing through this point. The point of intersection gives the point that represents 1, 5. In the same way, mark the points corresponding to the different sets of values as shown in the image. Join all the points on the graph. It is a straight line which is the distance time graph for the motion of the car. If the distance time graph is a straight line, it indicates that the object is moving with a constant speed, that is uniform motion. However, if the speed of the object keeps changing, the graph can be of any shape, that is non-uniform motion. So, we can say that the distance time graph indicates the type of motion, whether it is uniform motion or non-uniform motion. Hence, we can conclude that the distance time graph gives information about the distance covered by an object in a definite time interval and also the distance covered by an object at any instant of time. Now let us know the procedure to calculate the speed using distance time graph. The distance time graph can also be used to find the speed of an object at any instant of time. To find the speed of an object, consider a small part AB of the distance time graph shown on the screen. Draw a line parallel to the x-axis from point A and another line parallel to the y-axis from point B. These two lines meet each other at point C to form a triangle ABC. Now on the graph, AC denotes the time interval T2 minus T1 while BC corresponds to the distance S2 minus S1. From the graph, it can be observed that in time interval T2 minus T1, the object traveled a distance equal to S2 minus S1. Then, the average speed of the car is S2 minus S1 by T2 minus T1. Speed gives the idea of how fast the body moves. In general, bodies move in a particular direction at an instant of interest, and this direction may not be constant throughout the journey. Here we will know about the velocity time graph. The change in the velocity of an object with time can be represented on the velocity time graph. In this graph, velocity is taken on the y-axis and time is taken on the x-axis. Case 1. For an object moving with uniform velocity, the graph will be a straight line parallel to the x-axis. This is because the velocity does not change with time. The distance traveled by the object between the points A and B with velocity 20 km per hour is determined by the following steps. We know that velocity is the ratio between speed and time. So, speed equals to velocity into time. Here, v equal to 20 km per hour equal to AC or BD. T equals to T2 minus T1. Therefore, S equals to AC into T2 minus T1, which equals to AC into CD. S is equals to area of the rectangle ABCD. Case 2. For an object whose velocity is increasing with time, the graph is a straight line having an increasing slope. This is because the velocity increases by equal amounts with equal intervals of time. The area under the velocity time graph is the distance, that is magnitude of displacement of the object. The distance traveled by an object between the points A and E is the area ABCDE under the velocity time graph. It implies S equals to area of ABCDE. Implies to S equals to area of ABCDE. This is S equal to area of rectangle ABCD plus area of triangle ADE. Implies to S equals to AB into BC plus half into AD into DE. Case 3. For an object whose velocity is decreasing with time, the graph is a straight line having a decreasing slope. This is because the velocity decreases by equal amounts in equal intervals of time. Case 4. For an object whose velocity is non-uniform, the graph shows different variations. This is because the velocity changes by unequal amounts in equal intervals of time. Now, let us see the equations of motions by graphical method. The motion of a body moving with uniform acceleration can be described with the help of three equations called equations of motion. The equations of motion are V is equals to U plus AT, S is equal to UT plus half AT square, V square minus U square is equals to 2AS. Click each tab to know more. Equation for velocity time relation. V is equals to U plus AT. Consider a velocity time graph for a body moving with uniform acceleration A. The initial velocity of the body is U at A and it reaches a final velocity V at B in time t. Draw the perpendicular lines BC and BE from point B to the time and velocity axis, so that the initial velocity is OA, final velocity is BC, and time interval is OC. Now draw a line AD parallel to OC. We observe that BC equals to BD plus DC, which equals to BD plus OA. Substituting BC equals to V and OA equals to U. Then we get V equals to BD plus U. Implies to BD equals to V minus U. Acceleration equals to change in velocity by time. A equals to BD by AD, that equals to BD by OC, which equals to V minus U by T. Implies to AT equal to V minus U. Implies to V equal to U plus AT. Equation for position time relation. S is equals to UT plus half AT square. Consider a velocity time graph for a body moving with uniform acceleration A traveling a distance S in time t. The distance traveled by the object between the points A and B is the area OABC, which is a trapezium. That implies to S equal to area of OABC. Implies to S equal to area of rectangle OADC plus area of triangle ABD. That implies to S equal to OA into OC plus half into AD into BD. Substituting OA equals to U, OC equals to AD equals to T, and BD equals to V minus U, which equals to AT. Therefore, we get S equals to U into T plus half into T into AT. That implies to S is equal to UT plus half AT square. Equation for position-velocity relation V square minus U square equal to 2AS. Consider a velocity time graph for a body moving with uniform acceleration A, traveling a distance s in time t. The distance traveled by the object between the points A and B is the area OABC, which is a trapezium. That implies to S equal to area of trapezium OABC. S equals to OA plus BC into OC by 2. Substituting OA equal to U, BC equal to V, and OC equal to T. We get S equals to U plus V into T by 2. From velocity-time relation, T equals to V minus U by A. Therefore, S equals to U plus V into V minus U by 2A, which equals to V square minus U square is equals to 2AS. Follow-up work. Suggest few examples for motion of an object where its speed remains constant but velocity changes. What is the displacement of the body if it returns to same point where it is started? Give one example in daily life. You have successfully completed the chapter Motion.